Welcome back to Core Ideas, the podcast interested in all things related to lake sediments and paleolimnology. My name is Adam Jeziorski, and as always, I'm here with my good friend Josh Steamboat.
How's it going? Do you think anyone noticed the slight name revision on the podcast, that we're now Core Ideas, the paleolimnology podcast?
Probably not until you pointed it out, but I think it's deserved. 2 years in, 41 episodes in the bank, and there's no one nipping at our heels to compete for the title of the paleolimnology podcast.
It's true. It was important to get that done before we decided on the t-shirts and the merchandise. I don't want to be a paleolimnology podcast on the shirts, so I think that was the right call.
Not just one of many.
That's right. All right. What shall we talk about today, my friend?
Well, given that our current arc is called Conceptual Rabbit Holes, kind of look into another sort of off-the-wall, mind-bending topic within, not really paleolimnology as a whole, or not specific to paleolimnology, I guess. Some aspects of paleolimnology that are kind of are particularly interesting the more that you think about them. And so I was thinking with today's episode, we would take a look at how the scales involved can really get a little weird when you start dealing with microorganisms and microenvironments. So we're looking to some questions of scale.
Sounds good. Yeah, it's one of those weird things, right? Because generally in paleo, we're interested in little things like small fossils, all those kind of things. But they're there in huge numbers and they're living in huge spaces for them. And that's a bit of a conundrum. Not a conundrum for them. It doesn't affect their existence. They don't know that, but...
Or care.
But for the paleolimnologist, it is a weird relationship. Sometimes it may be important from a methodological perspective, but it is an interesting thing to ponder when you go down one of these rabbit holes. So let's do it.
Absolutely. And so in terms of the relationships looking, I think, you can come at them from the perspectives of the spaces involved, the densities or concentrations involved, and especially at the end. And then it does get more paleo specific, the time scales involved. Mm-hmm. But I think maybe just kind of start with like size and space, and kind of involves a bit of a slight detour into the world of oceanography.
Yep.
Which is something I don't know very much about. But diatoms, as like the classic example or the type organism of paleolimnology in many ways, are individually incredibly small, ranging in size from 2 to 200 micrometers. But despite that, they make up a significant fraction of the Earth's biomass. And I was kind of like blown away when you start looking for references and just estimates of how important they are to life on Earth, that they generate 20 to as high as 50% of the world's oxygen.
Yeah.
Which I'm not sure I believe, but that it goes that high, the 20%, like a full half, seems absolutely incredible to me. But I guess, yeah.
Oh, for sure. That's one of those facts that, you read and you say in lectures. I say that often in lectures because it's always a good idea to talk about diatoms. Mm-hmm. It makes me excited. And people just look at you like you're completely crazy. It's like, what about the trees in the Amazon and all of the other plants and those organisms? Those ones would make sense, right? It would make sense that trees that are 3 feet, 4 feet, 10 feet across produce a butt ton of oxygen. But
tiny, a lot of tiny diatoms into 10 feet across.
You can, and the ocean covers a pretty significant portion of our Earth. Yeah. So that's one of those crazy things of scale. There's so many of them, and it's 3-dimensional. The photic zone in the ocean can extend a decent way down, so you get a huge area. Huge volume,
Yeah.
I mean.
And yeah, there are lots and lots and lots of, even just those tiny things. And then just again, to like wrap your head around the scale is the fact that, there are layers of diatomaceous, I'm not gonna be able to say this right, diatomaceous earth.
Nailed it.
On the ocean floor, or piled up on the ocean floor, that it's a mineable resource.
Yeah, for sure. And not one that's like rare. You don't have, it's not like diamonds. That's a mineable resource that you pay an incredible amount of money for each of them. You can go to the garden center and buy it in squirt bottles that you can then put around your plants to keep the slugs away or whatever they're for. I don't know. Yeah, huge quantities. Yep. Just sitting on the ocean floor, ready to be harvested, dried,
And it's just packs
sold
and
for
packs
$8 a bottle.
Ancient diatoms.
Yeah, exactly. Like pure diatoms. There's some pretty cool videos online or pictures or whatever of people taking like a smear of diatomaceous earth and putting on a microscope slide. I've never actually tried to do it. But yeah, just exactly what you would expect. No different than a really concentrated slide from a lake core or something, just different species.
And so this will be the theme of the episode, because questions of scale, and particularly, especially at the beginning when you first, or at least I thought, at the first introduction to paleo as a grad student, the physics of size come up again and again and again. And I did my, not all of my early years, but some of my early years in paleo were on the zooplankton side of things, looking at Cladocera. And there was like just a general anecdote from my supervisor that really stuck with me when I was first talking about doing like zooplankton net hauls. And just the idea is like, because like you can see a Daphnia, it's got a black eye spot, and it's visually dodging things and moving out of the way when things come out towards it. And I just asked like, the fairly obvious question is like, so what's like, I'm trying to scoop up these diatoms with this net that's like 30 centimeters across.
Daphnia. It was Cladocera. Yeah.
Yeah. What's stopping them just moving out of the way? Like, how do I know I have a representative sample? And he said something along the lines of, yeah, well, it doesn't really matter. It's the equivalent of if, like, aliens started doing football field sized dredges of the earth at the speed of sound. You can run all you want, but you're not getting out of the way of it. And I never checked the math to see if it was equivalent at all, but the imagery really stuck with me.
Oh, it's a great example. Even if it's an order or two of magnitude off, it still gets the point across, though, right? And sounds great. Like, it's a great thing that you can say over and over to students, and they can perpetuate it. Now they put it on their podcasts, and everyone says it because
it's true. It's on the internet, so it's
yeah,
true.
Exactly. So because it gives you that visual that the scale is so completely different. Even if it's not a football field sized dredge, even if it's the size of a dump truck, it doesn't matter. The scale is outside of your range that you experience on a day-to-day basis, and that's exactly what it is for those Daphnia or whatever, as it would be for you if aliens came and started scooping up the planet. It's a great example of like science communication and how it can work.
Yeah. And just thinking of like, just from the perspective of just hand-powered motion through the water for the scale of these guys is just orders of magnitude beyond their abilities to react.
For sure.
Or comprehend in the equivalent sense.
Yeah, and then we'll talk about, I think in a minute, when we think about the medium itself, and that compounds all of those differences as well, because how you experience the environment depends on the scale that you exist at. But a few more examples maybe before we leave this scale size, or the size part of the scale. What else can we think about here that are important? And maybe from a aquatic but paleo perspective.
Yeah. Well, it's still within the realms of aquatic and zooplankton, cladoceran, and in insects and things. The idea of gate limited aspects of predation being a key to survival. That you want to be big enough that you're more than a mouthful for some of the like the grasping insects and larger zooplankton. but you can't. But at the same time, you can't be too big. Or you become an easy prey for the fish that can snap you in one bite. But there's some pretty cool high-speed videos out there of like chaobrous attacks and failed attacks.
Oh, yeah.
And like, I don't know what the word would be. It's like super slow motion, like super high frame rate recordings, and just to see the massive speed that they snap at like a Bosmina or something and launch themselves. And on side note, a human-scaled chaobrous would be absolutely terrifying.
Holy
Those are
Jesus.
mean-looking creatures.
Very much so. Like alien, very alien proportions. Like, you couldn't design such a thing for the next Predator-like movie or Alien-like movie. Yeah. And actually, that's something we hadn't really talked about that made me think of it. The idea of speed and velocity and how that plays into this whole thing, because there are lots of videos on the internet from research or just kind of, again, SciComm examples using high speed cameras, really high frame rate cameras, to look at biological organisms doing things very quickly, because some, especially small organisms, can move at incredible rates compared to what we visualize. It's all relative to the size again, because they're moving very, very small distances in very, very short amounts of time. Of course, you can move further if you swing your arms, but you're moving very slow relatively. And those kind of food grasping activities, or the injection of like venomous compounds and that kind of process, can occur at like rates that are impossible to see with the naked eye, or at the frame rate that we visualize things. Yep.
Absolutely. And then at the same time, you have like the that you have the incredibly rapid speed, again staying within the realm of zooplankton. You would have Pithetrephes, who we would have talked about a little bit last episode as an invasive species, will be another one of these predatory zooplanktons. And it's got this well-deserved reputation as an absolutely voracious predator, in terms of it absolutely decimates the large zooplankton that it runs into in a particular lake when it's introduced. But then seeing them in aquatic, like captured. And I remember working, not with a student, but in the vicinity of a student that was trying to rear Bitho in culture. They're incredibly lame looking swimmers. It's the opposite effect of like they just kind of dipsy doodle through the water at a fairly whirligig kind of motion, kind of speed. But they just never stop, and there's lots of them, and they just eat everything they bump into, more so than actively hunt things down. And yet that is enough to decimate an ecosystem. Just the rate
they're not seeking
things
out, because there's so many food items to consume, and they're voracious when they get to them. They don't have to put that time into being more raptorial, seeking out items. Yeah. Another interesting example of the fact that, I don't know, just a lot of these things are just cool examples of biology making sense at these different scales. In that environment, you don't have to be a great swimmer. You don't need to put energy into that. And it seems to work out quite well, especially when you get introduced to a novel environment.
Oh, and in terms of novelty, one that I thought, if we're talking about predator avoidance, and again, we've been, zooplankton heavy in this introductory segment, but the idea of transparency as a predator avoidance, which is a thing that would not scale up to any real size. It only works. I guess there are transparent fishes, I guess, but
yeah,
I don't think it's not quite transparent on the same scale as like a Daphnia, where you see right through them, and
it's more coloring.
Yeah, it doesn't scale all the way up, like, because if you had transparent zebras running around the Serengeti, it really wouldn't work, because it'd still be looking like there's like green snakes floating through the air in terms of their digestive systems, which you can see on a on a Daphnia, but it works a little bit better because it's still a fraction of a Daphnia.
It would be an interesting world, though. I mean, that'd be something to see, wouldn't it? Yeah, you're right. The transparency. I mean, also the idea that this is very zooplankton specific. I think they're an interesting comparison because they're like big enough that some of the things, predation and stuff like that, make sense in the same sense that we think of them, but they're also very small. So they're a good intermediate step. Hence why they're good paleo indicators. But yeah, the transparency is an interesting one. I don't think it's the same for fish. Like there are very few truly transparent organisms. When you get into the deep ocean, things get weird. When you get into cave environments, those kind of places. But I think more it's a like coloring perspective that's different. So true transparency doesn't really scale up.
If it did, it'd be cool. Like imagine seeing like the giant herd of transparent wildebeest, like running down Simba.
Seeing in air quotes.
Snakes.
Yeah, exactly.
Yeah.
Huh. There you go.
Okay. So moving beyond just size differences and small things, can also like combine that with concentrations and densities because at microscales, these also become very interesting and in many ways are foundational to paleo in general, but are interesting in and of themselves. One that really jumps out that we talked about not too long ago would be the concept of isotope fractionation, which I think, is another one of those things where you just take it at face value and it's like, yeah, it's a mathematical relationship, yada, yada, yada. But when you start talking about things like, oxygen hydrogen isotopes and the idea of like the differential evaporation rates based on the one extra neutron of mass on a particular molecule, like
it's crazy. Yeah.
You're not getting much smaller than that in terms of scale, I guess. And then when having that at planetary scales in terms of like the influence on being able to track hydrologic regimes and, global meteoric water lines. And all this comes down to lots and lots and lots and lots and lots of single neutrons. That's
right. Just a little bit more neutron or a little bit less. Yeah, or just how different they behave. Like the fact that something with, well, I guess we talked about this in the episode, that hydrogen is the most different. So maybe like talking about the difference between lead 206 and 208 is a better example, but it's easier to visualize for hydrogens. That tritium is so completely different than deuterium, than protium, all based on one single atomic mass unit difference. That I don't think there's a smaller scale example of these kind of, I guess, concentration at the broadest sense, mass differences that you can come up with. And you take it for granted. It's like, yeah, that's how it works. So, that's physics. That's chemistry, whatever it is.
Yeah, and then the scales involved. And, you were talking about when we were like brainstorming the episode of like recently working on like mercury dilutions and, the process of getting down to a 1 part per million solution. And, it's like, when you're doing something by 10 by 10 by 10 by 10 by 10, it takes a while.
It takes a while. And, we were just calibrating some instruments that have been sitting for 2+ years during the pandemic that need to be brought back online, thankfully. And preparing, you buy a stock standard that's very low concentrations of something known from a laboratory or from a chemical supplier. And then you dilute that down and you dilute it again. And you really come up against limitations of instruments, right? The accuracy of the scale, the precision of the pipettes or syringes you're using, all of those things, and tiny, tiny differences in that can perpetuate. So you're trying to make a stock solution or a solution of 1 part per million, and you get a tiny little bit more in, and it changes all of those numbers, and you can account for all those things. But the tiny fractions of chemical concentrations can be very, very small, but also can perpetuate these kind of not errors, but issues associated with the instruments and that kind of thing. And then if you can kind of scale up those tiny values and think about, like what the difference is between a lake that has 2 microliters of phosphorus, a very oligotrophic lake, and one that's 10 times higher, and because you often do a 10 times dilution or something like that. That's a completely different environment, completely different lake. The organisms living there are different. The processes are different. The relationship between organisms in their environment completely different by one dilution, in the lab sense.
And then you go up one more and it's completely unrecognizable.
Right.
It's like a 200. And then even to the naked eye, it's like crystal clear versus swamp. And it's a 2 orders of magnitude thing. And in many of these scales, you're dealing with many more orders of magnitude than that, and in terms of the scale being examined.
Right. Yeah. Like pH, right? So that's 2 orders of magnitude, but pH is a log scale. So the difference between 5 and 7, most people can't visually, obviously, it's a different variable, but like the difference between 5 and 7 is not all that significant. There's environmental differences, but not to the same as 0.2 to 200 micrograms per liter of phosphorus.
And then that not translates, but you can very easily follow a thread of ideas from there into the depletion of resources, whether they're either low to begin with or depleted through some sort of boom-bust cycles, and how little changes can be in terms of, you're just talking about oligotrophic versus eutrophic conditions, but in terms of tipping the scales from one system to another, can be quite small in many ways. And when you talk about things like silica limitation, and that can, you can have diatom blooms in low silica environments that have been essentially suck all the available silica out of the water system completely.
Yep. Those are we've talked about this a bunch of times, and I think I say it every time. It's some of my favorite sort of paleo examples of that, where you have this normal system kind of chugging along, diatom's doing really great because there's lots of nutrients, but they also need all these other things, and then they drain all of the silica out of the system, and that limits their growth. And I think one of the really interesting things is to tie back to the idea of the size relationship that they have, and that this doesn't have to mean the entire lake is drained of its environmental variable, silica, for example. They have such a small microenvironment that organisms sometimes live in. It might be habitat based, it might be just environmental kind of around them, that the pockets for these depletions or enrichments or whatever are not lake scale necessarily. In a well-mixed system, perhaps, but in others, no, they could be very, very small. That habitable zone around that single diatom is only going to be measured in millimeters or less, centimeters at the absolute outside. So it doesn't really matter if it's outside of their reach.
Yeah, the diatom's not going to pick up and go, I'm like starving of silicon here. I'm going to walk over to the other side of the lake. It's like they're only moving a tiny fraction of distance, and that limited movement creates all kinds of microenvironments where, in terms of, as you mentioned, depletion or enrichment, where conditions may be, absolutely perfect in the immediate vicinity, but like a couple of millimeters, a centimeter away, might be incredibly hostile to the same organism.
Mm-hmm.
And blissfully unaware of that difference.
For sure. Yeah. And some of the work we did in Yellowknife, where the lakes that we've talked about, where the lakes were contaminated by arsenic, pollution from mining. One of the really interesting findings was that the diatoms in the water column seemed to suffer more. They relatively decreased associated with an increase in more benthic taxa. And one of our thoughts on that was that the benthic environment is probably a little bit more protected. They're in the water column, they're more exposed to this arsenic, it's more mixed. In the benthic zone, there's biofilms of bacteria that are able to detoxify or protect relatively the species living there. So that might be a location that is just a little bit more hospitable to everything, but maybe diatoms included.
Yeah. Yeah, and those environments, they are those drastic differences between environments occur all over the place. Lakes are very, that's what I'm looking for. Heterogeneous environments in terms of you've got your water column, the benthic substrate, the macrophytes, but when you get down to the real granular nature, it's like certain macrophytes may be releasing certain nutrients or whatnot in the immediate vicinity. So we get these really pockets all over the place that we often just gloss together as the lake.
Or the other way, they're allelopathic, they're producing things that are toxic to other organisms, including other macrophytes. Like there's just so much variability in natural systems, and so much competition that the differences of a couple centimeters in water depth could completely favor a different taxon because of those different abilities to really thrive in those conditions. And that's within one lake. Like you go to the river mouth that's feeding into that system, grading up to a completely different river environment, going down to the marine environment. It's a messy world out there.
It boggles the mind.
Yeah. Things you just sit and think about, you're like, oh my goodness.
Yeah. It's like, these are definitely rabbit holes you can go down when you start thinking more and more about it. And then in terms of concentration and density, the most obvious one, and you mentioned it in segment 1, but it would just be within the water itself. And the idea of like the water reaching its maximum density at 4 degrees Celsius impacts everything in terms of aquatic environments, stratification, things like surface tension, but like the whole idea that lakes freeze from the top down for a reason, because it's coldest up at the surface. And if it wasn't for that, and you had situations where, lakes froze from the bottom up, the world would look very, very different. It would suck to be a fish in Arctic environments.
Yes,
lakes
it
that
would.
froze from the bottom.
It would suck to be something that evolved from a fish as well.
I evolved from a fish.
That's what I mean. Yeah, it would suck for us. We probably wouldn't have this wonderful podcast.
Or it'd be very different.
Yeah, exactly. And that's a fundamental property of all aquatic science. And the density thing just continues. The movement of we have a very human centric, obviously, view of our environment and how we interact with it, and the difference in the density of water from air. For example, when you're walking around in air and then you get into the swimming pool, you feel that difference. It's a lot harder to move. Some people move very efficiently through that medium, others not so much. But that's our mass relative to the density of water. If you're a Chaabris or a Daphnia, that's entirely different. They have or a rotifer, those kind of things. It's like swimming through syrup or treacle for us or more. And then go to the other side, a blue whale's completely different from us too. Like their interaction with water is totally different from ours. So it's all relative.
Yeah, and like the biggest animals in the world, diet is completely dependent on teeny weeny animals.
Yeah. Blue whales are an interesting kind of, well, all of the baleen whales are like that. Yeah, they survive on like little krill and other invertebrates and whatever else they can vacuum up in their giant mouths. But they do have those organisms that they're feeding on perceive the environment in an entirely different manner than they do.
Yeah. Yeah, and just rolling back to the water density ties into the issue of our times, like climate warming and the impacts that warmer temperatures have on increased water column stability. And then you're seeing just shifts among like diatom communities when the whole idea is, or not the whole idea, diatom taxa, as we mentioned earlier, they're not moving actively on their own, or not very many of them are motile at all. And they're completely relying on turbulence within the water to remain in the photic zone. Because if they drop below the photic zone, that's a death sentence. Once they're out of the light, they're going to starve to death, and there's no coming back up when you drop below that thermocline. So, if like sinking out is, the worst thing that can happen to you, the bigger, heavier ones become more disadvantaged as stratification becomes stronger and because they require more turbulence to stay in the life zone.
Yep, the life zone. Yeah, I like it. Yeah, exactly. And we see that at a global scale. Anywhere that's warming and getting to be less turbulent, greater stability in the column, the water column. You can see a shift in the species able to better occupy that niche and survive in that environment, and the loss of the others that can't.
And then again, at the small scales, water tension can also be an impenetrable barrier. So you've got the density barrier of like the thermocline, but then also if for whatever reason they're brought up above the surface, then there's no getting back down either, or vice versa, in terms of being stuck on the top of or the outside of a bubble or things like that. And some organisms are able to use the water tension to great effect, but for the really small ones, there's, it's something they're at the mercy of.
Yeah, there's a whole community, obviously, living associated with the transition between air and water, the Newston, whatever, however you say it, community. Some living on top, like the water striders, and then others that live in the water at that
bottom
interface.
Side.
Yep, the bottom side, exactly. And that's actually what you don't really think that much about, eh? It's less, less commonly studied. Perhaps it's a very interesting environment, but a huge, an advantage, a usable environment for some if you want to stay at the surface and attach to that surface tension, or
you don't have to worry about the turbulence then.
Yeah, exactly. But definitely one that can be a barrier in the same way as any of the others for organisms not well adapted to that. Yeah.
Cool beans.
Yeah, no kidding. Like, you could just continue talking about this forever. Like the difference in the environment for organisms at every kind of level. We haven't really talked about, we talked about algae, obviously. We haven't talked about plants all that much other than their sort of chemistry environment. But the fact that macrophytes exist in, or that can continue to go about their activities in an aquatic environment is entirely because they live in water. If you take a macrophyte, most people have probably done this and are trying to ID them, or you're moving them to a different location or whatever, and take them out of the water and they're just a pile of green goop on the dock or in the bucket or whatever. It's the water that gives them their structure. It's because of the density of water that they stand up in the water column into
float on
the
top.
photic zone or float on top. That's right. Yeah, exactly. And they could take advantage of that sometimes with like air vesicles and those kind of things, but they are adapted to a totally different environment, just as we're adapted to an air environment. And this is something we talk about a lot. Like I talk about a lot in some of my classes, is the fact that the properties are what makes it different. The processes that are occurring are all the same. You know, the processes of movement of these fluids is exactly the same. They're driven by velocity and the thickness of the environment and all of those things. So whether you're in air or water or liquid ethane on the moons of Titan, all just depend on the density of the fluid you find yourself in.
Okay. Are we going to start talking about the paleolimnology of other planets?
Maybe not in this episode. I think we're moving along. We should probably move on to time, where we do have something to say. But there is a lot of connection to, well, using these kind of physical processes in other worlds broadly, but the paleo world as well. So maybe down the road we'll have an episode on it.
Well, maybe we'll invite Elon Musk on to talk about
it. Yeah, sure.
And the final big category in terms of scales that I thought we should talk about today is one we actually talk about quite a lot on the show, would be temporal scales, just because they're really interesting, I think, in paleo because of the extremes in both directions. On the one hand, in a single study, you'll be reliant on things like on the scale of geologic time in terms of the actual deposition of the core, depending on the time scale you're walking at. If you're doing like a Holocene core, we're talking like 10,000 years.
Or the isotope stuff you were talking about before, like the breakdown of those isotopes are part of this geological sequence. So it's in every example for sure.
But then at the same time, so that is your, I guess, measuring stick, your temporal measuring stick. But at the same time, you are analyzing, in the diatom example, organisms that are going through a generation time of hours to days. And both can be really mind-bending because you're heavily reliant on both. And one of them is so short as to kind of be hard to really comprehend. And the other one is so long as to be hard to really comprehend. And, the purpose of every paleolimnological analysis is really to bring those two things together to say something useful about change through time.
Yeah. It's the perfect, I don't know, intermediary, stepping stone, whatever it is, to give people the ability or the opportunity to think about both of those kind of scales and really rely on both of those scales. And it only works because you're bridging that not bridging the gap, but using both of those time frames. Small scale, so you can rapidly, what do we talk about what a good paleo indicator is? Small scale organisms, rapid environmental change times. Greenland sharks make a bad paleo indicator. But on the geological time scale, you can get the long history of this environment.
Yeah. And that kind of, Holocene to diatom generation time, I think, would be covered in most paleo analyses in some way, but then you can scale up to real extremes when you start looking at, depending on the radioisotopes you're working with, like some of the really short-lived ones that you wouldn't be necessarily working with, but, exposed to via the literature. You talk about half-lives of femtoseconds. And then, the stable isotopes, you're looking at the age of the planet for their half-lives.
Sure. Yeah, they may be radioactive, but the planet's only 4.6 billion years old. So we haven't gotten long enough to see them decrease in abundance. Yeah, exactly. It's down to the smallest units of time that have ever been imagined.
Yep. And I think this is really interesting on a whole bunch of levels because, you're putting those two things together, and and you're just collating into individual sediment slices. So sticking with the diatom example, you're going from generation times of days, but you're really looking at it coalescing into seasons and capturing bloom differences through time. And then depending on the deposition scale that you're working on, there might be multiple annual cycles compressed into a single sediment slice that you're working with, but you're still working with very small things. And and looking at those changes averaged through time. And again, another quote, I have no idea where this one came from or idea where I first heard it, but it seems to like tie into all of this stuff, is just in general how and society or humans or just people in general seem to always massively overestimate how much things can change in a single year and underestimate how much they can change in a decade. And like a single sediment slice can, you can see incredibly abrupt changes, even, in a single season quite easily in paleolimnological analyses.
Yeah, I think that's a great quote. And it really makes sense. Like people, again, just as we have this space, density, whatever, perspective, we have a temporal one, and I don't know what it is. It probably depends on the person a little bit, but generally we think in the range of less than a decade. Probably we think about that. It's how our news cycle works, where it's tied into our elections and all of those kind of things. And even if you scale it up to a generation, which is 25 years or something like that on average, we do have a very specific view that's not very long, but also not very short, fitting with our life cycle. I did some back of the napkin sitting here calculations when we were thinking about this, and that depends what source you read, but there's been 7,500 human generations since our species evolved. And if you think about the diatoms with a generation time of, I don't know, a week, a day, those kind of numbers, all of those 7,500 generations could be in a single sediment core that's 150 years of time, which is a long time for the diatoms, but not that long for us. And diatoms evolved in the Jurassic period, right? So that's 100 million years ago. Just think of how many generations there are and how they're, again, humans are not a very good paleo indicator either, because of that as well. So get some interesting comparisons.
So far.
Maybe for those aliens who exist on totally different timescales,
Yeah. And are dredging the planet at the speed of sound.
Mm-hmm. Yep. Or we're in a microcosm that they're manipulating.
Yeah. And and generation times, anyone that has done any kind of paleo analysis can have a good sense of how quickly adaptation can occur. Thinking back to, if conditions become unfavorable, they disappear fairly quickly, and vice versa. And if you look at any kind of study looking at tree lines, it's just like in and out of particular taxa associated with a particular environment. And you don't have to be talking about paleolimnology as a science. Just even a single course study can give real insights into the pace of adaptation and community responses to ecological change.
Yeah, it's one of the ways we know that paleo works. Because we see these abrupt changes to changing conditions that we know have occurred, the organisms respond, and that means we can track them under the right conditions.
All right. So, yeah. So, I don't know about you, dear listener, but try to expand your mind. We need some mind-blown gifts associated with this episode somehow. But I think I'd just sort of end on, a little bit of a more romantic note. But I think in terms of the scales involved, paleolimnology has to be among a fairly small group of scientific fields that are concerned with such extremities of scales in both directions. And I mean, obviously, physics, yes. But I don't think there's very many individual physicists, let's say, that are necessarily interested in both such very small things in very large amounts over very long time scales, responding to their immediate environments. There's a definite uniqueness to all of it in terms of pulling it all together. That paleolimnology and stands apart in some ways. And maybe I'm wrong. Maybe there are some other examples that people could pin it to, but I couldn't think of any. For whatever.
Yeah, there may be, but it is a really good one. And one that really relies heavily on it, which we said, and just highlights the utility of not worldview, a view that takes into account all of these differences.
Yeah. And, that's what makes it cool and interesting and drew me into it in the first place was, diving headfirst into some of these rabbit holes and, just being like, whoa.
And perhaps got you, dear listener, 47 minutes into two guys rambling about the scale of the universe. So thanks for listening. Yes.
So once again, this has been Core Ideas, the paleolimnology podcast. And if you have any questions or comments, or perhaps a suggestion for a future show, just please send us a note.
Our email address is coreideaspodcast@gmail.com, or you can reach out to us on our Twitter handle @coreideaspaleo. We read everything that you send us eventually.
Yes, we definitely don't have our fingers on the pulse of social media, but we will eventually get caught up and respond to you at most a week after the fact. An archive of our past episodes and show notes for many of those episodes is maintained on our website at coreideas.ajaziorsky.ca. The link is listed in our Twitter bio.
And if you are so inclined, you can give us a rating, subscribe, leave us a comment on Apple Podcasts, Google Play, SoundCloud, wherever you get your podcasts. We really like reading those. The 5-star ratings are great, but in the end, we do this for fun, so they're just a little extra.
And that's it for today. But we'll be back soon to explore another conceptual rabbit hole related to paleolimnology, sticking to our ethos of pure knowledge without the economy.